as I told you yesterday, I think, now is when we get into the calculus of vector-valued functions. So today, specifically, we're going to be looking at derivatives and integrals of vector functions or vector-valued functions. Are you excited?
I'm so excited.
I'm really excited, too. We're going to start with derivatives. Of course, when you start talking about a derivative, you have to look at the definition. Do we remember the definition of a derivative? Ooh, okay. So let's say if r of t is a vector-valued function, or like we said, you also can call it a vector function, the derivative of r with respect to, so wrt with respect to t is, okay, so first of all, the notation, you could see that. You could see r prime of t. You could see dr dt. You could see d dt of r of t. So that's the notation. Okay, definition of a derivative from last year. Not what does the derivative mean, but when you first learned derivatives, how did you find one? Using a limit. So I'm going to do the limit as h goes to 0. Anyone the denominator? H. Okay. Whew. Numerator? Does that look familiar? Okay. Mostly I'm not going to have you use that. So we're going to look at what this looks like geometrically, and then I'm going to give you a theorem to help you find the derivative a little bit easier. Okay, so geometrically, let's say that we have some curve like this. We're going to choose 2 points on that curve. Let's say the first vector is r of t. And then the vector that goes to the second point is r of t plus h. This difference then on the x-axis is our h. When we connect to the first point to the second point, that is r of t plus h, subtract r of t. What do we call that red part? So, yeah, that's what I was looking for. This is an example of a secant. You guys remember that? Yeah. Secant connects 2 points. Okay, so then draw the same thing again. You still have your curve. You have your 2 points. Okay, so we still have that secant. The derivative at this point looks something like this. So that'll be r prime of t. So if you remember, the derivative gives you a tangent. So r prime of t is a vector that is tangent to the parameter curve. It's at the tip of r of t. Here's why you need that second point, is the vector tangent is going to point in the direction of increasing parameter. So we start at the tip of the first vector and we point in the direction of increasing parameter. So that should make sense. That should be similar to what you guys have done with derivatives in the past. Okay, so like I said, I'm not going to have you use this definition most of the time. You're going to use this next theorem. So practically, how are we going to calculate the derivative? If r of t is the vector valued function with component functions f of t, g of t, and h of t, where f, g, and h are differentiable functions, then r prime of t, if I want to find the derivative of r, I can take the derivative of each of the individual vector valued functions, or individual component functions. Okay. Questions so far? Okay. Well, you should be asking me one question. Do you guys just trust me that this is the case? Why? You shouldn't just trust me. Haven't I been wrong before? You're going to take my word? Well, if you notice, our second objective for the day is a proof. So I'm expecting you to know how to prove this theorem. So we're going to prove it. Okay. As always, you're going to start out your proof defining any parameters. We are going to prove this in 2 space. Proving it in 3 space is very similar. So let's say that r of t is a vector valued function. Let's call it its component functions, x of t and y of t. If I want to find then r prime of t, I can't use this theorem because I have to prove that theorem. So what am I going to do instead? Use the definition. So this is the limit as h approaches 0. Okay, in the numerator, it's r of t plus h. So that's going to be x of t plus h I plus y of t plus h j. So that's r of t plus h minus x of t I plus y of t j. All of that over h. We're going to rearrange some terms a little bit. So this is really the limit as h approaches 0. Bring all of your x's together. So we get x of t plus h minus x of t over h. That entire quantity times I. Plus the limit as h approaches 0, bringing your y's together. Sorry, I guess like that, really. Of y of t plus h minus y of t over h. That whole limit times j. This is x prime of t times I. That is y prime of t times j. So all you did is you used the definition of the derivative on r of t, then you brought your x's together, your y's together. And now you have the individual derivatives of x and y. Okay, questions? Great. Example 1. R of t is going to be 1 over ti, add e to the 2tj, subtract 2 cosine of pi t multiplied by k. We're going to find the derivative. So like we said, you're just going to take the derivative of each of the component functions. That's the first function, that's the second function, that is the third function. Derivative of 1 over t is negative 1 over t squared, and then times I, plus 2e to the 2t times j. Derivative of cosine is negative sine, so the derivative of negative cosine is going to be positive sine. But then you have that pi because of the chain rule, so we get 2 pi sine of pi t times k. So that is your whole derivative. Questions? No? We're okay? Okay. Some vocab things I need you to know. R prime of t oftentimes will be referred to as the tangent vector. So we saw that in the picture on the first page of notes. You're also going to be asked to write equations of tangent lines. A tangent line is a line through some point P that is parallel to R prime of t. So R prime of t would give us the direction, and then P would be the point. Last piece of vocab is the unit tangent vector. Okay, unit tangent vector is denoted by big T of t. That's going to be the tangent vector R prime of t if we made it a unit vector. So we have to divide by the magnitude. That's a vector that you're going to do a lot with. Not this section, but eventually. Next example, I'm calling it example 1.5 because it goes with example 1. We are going to find the unit tangent vector for example number 1 at t equals 1. So unit tangent vector, that's capital T. We're looking specifically at t equals 1. So using this formula, that's going to be r prime of 1 divided by the magnitude of r prime of 1. We found r prime of t to be that negative 1 over t squared, comma 2e to the 2t, comma 2 pi sine of pi t. If we find r prime of 1, so we plug in 1, we get negative 1, 2e squared, and 0. If I find the magnitude of that, we get 1 plus 4e to the 4th, which does not simplify. So our unit tangent vector then, we're going to take r prime of 1, so this, divide by the magnitude. So we will get negative 1 over the square root of 1 plus 4e to the 4th. That's the first value. Second one is that 2e squared divided by the square root of 1 plus 4e to the 4th, comma 0. If you are interested in the decimals, it's 0.068, comma 0.998, comma 0. So that is our unit tangent vector. Questions? Comments? Am I moving too quickly for us? No? We're good? Okay, so we're okay to move on to another example? Great. Example 2. For the curve, r of t is equal to the square root of t times I plus 2 minus tj. I want us to sketch, nope, I want us to find r prime of t. It's the first thing I want us to do. Then I want us to sketch r of 1 and r prime of 1. Okay, so our r of t component functions are the square root of t and then 2 minus t. For r prime of t, for the first component function, it'll be 1 over 2 times the square root of t. The second one will be negative 1. Okay, so that's the first thing. Next thing I asked us was to sketch. So we're going to sketch r of 1 and r prime of 1. Now they're only going to make sense geometrically if we also have r of t. So I want us to sketch r of t first. So like we did yesterday, you would make a little table, plug in some values of t to get x and y. I'm going to plug in 0, 1, and 2. If I plug in 0, I get 0, 2. If I plug in 1, I get 1, 1. If I plug in 2, I get the square root of 2 and 0. So 0, 2, 1, 1, 2 square root of 2. So this is r of t. Okay. R of 1 is this vector right here when I plugged in 1. So this is r of 1. If I do r prime of 1, I'm going to get 1/2 comma negative 1. So that's going to start from the tip of the radius vector. So this is telling us I'm going to go over 1/2 and down negative 1. So it's about here. So if you can picture it at the origin, going over 1/2, down 1, but then moving it up so that it's in the right spot. Okay. Questions on that before we do another example? No? We can keep going? Okay. Next one. We are going to find parametric equations for the tangent line to the helix that has the equations x equals 2 cosine of t, y equals sine of t, and z equals t at the point 0, 1, pi over 2. Okay, so first thing, we know r of t. I'm going to write this in bracket notation because it's just going to be a little bit nicer. Is 2 cosine of t, comma sine of t, comma t. To write the equation of a line, we need a point and we need a parallel vector. We have a point, we need the parallel vector. Parallel vector will be r prime of t at whatever our point is. So if I take the derivative, I get negative 2 sine of t, comma cosine of t, comma 1. Okay, but we want r prime at whatever our t value is. So if we look at the point that we are given, that's when t equals pi over 2. You can tell by looking at the last one, z equals t. So t has to be pi over 2. So if we plug in then pi over 2, sine of pi over 2 is 1, so this ends up giving us negative 2. That'll give us a 0, and then we have a 1. That then is our tangent vector. So our line then is going to be r of t, our point, so that's the 0, 1, pi over 2, plus t times our tangent vector. I asked us, though, to write the equation of the line parametrically. So this will be x equals 0 minus 2t, y equals 1 plus 0t, z equals pi over 2 plus t. Okay. Questions on the equation of the tangent line? Okay, there's two ways I can ask you to write the equation of a tangent line. I might ask you at a specific point like I did here. I might ask you to write the general equation of a tangent line. So we're going to do that off here to the side so that you can see what it looks like. So general tangent line would be if I give you any value of t. You'd be able to plug it in and give me the equation of the tangent line. So we're going to get x equals y equals z equals. It's all going to be based on t. Everything about the helix is based on t. As we did up here, it would be a point and then the parallel vector. The point is going to come when you plug t into here. Okay, so our point then would be 2 cosine of t naught, sine of t naught, and t naught. So that t naught just means I'm plugging a value in for t. Parallel vector is going to come from here. Parallel vector is what's multiplied by t. So we would get plus t, because t stays there, times the parallel vector. So this will be negative 2 sine of t naught, plus t, in this case, cosine. So cosine of t naught, and then plus t times 1. So this is the general equation of any tangent line for this helix specifically. Okay, not difficult to write, but I want to make sure we understand what this is saying. Do we understand how to use this? So we specifically looking for the tangent line at t's pi over 2, so we could plug in pi over 2 for these, and we would get this answer. Okay. Questions before we go on? No? We're good? Okay. Next thing I want to talk about, all the differentiation rules. There are 6 of them. Some of them are going to be common sense, some of them are going to be helpful. First one, if I take the derivative of u of t added with v of t, so the sum of vector functions, that's the same as taking the derivatives of the two functions individually and then taking the sum. So that's one that should make sense. If I take the derivative of a constant multiplied by a vector valued function, that's the same as taking the derivative of the vector valued function and then multiplying by the constant. Next one. Let's say this time it's not a constant, but it's actually another function, f of t, multiplied by a vector valued function. This one is pretty intuitive. It's going to work just like the product rule did. So that's the same as taking the derivative of f, multiplying it by u. Sorry, there should not be a prime there. And then taking f of t and multiplying it by u prime of t. So that's just the product rule. So like I said, those are the ones that are going to be intuitive. These ones are not as intuitive. Let's say I take the derivative of a dot product. So u of t dotted with v of t. Okay, the way to do that, you're going to take the derivative of the first function u and dot it with v. Then you're going to take the sum of u dotted with v prime of t. Next one would be this time if we have a cross product. Okay. If we have a cross product, you're going to take u prime of t and cross it with v of t. You're going to add with that u of t crossed with v prime of t. Last one, if I take the derivative of u of f of t, so a composite function, take u prime of f of t, and then you're going to multiply it by f prime of t. So that's just the chain rule. Okay, for 4 and 5, on 4, does it matter the order in which I dot those two? No. In 5, does it matter the order in which I cross the two? Yes. So please make sure you pay attention with the cross product that you cross in the right direction. Okay, theorem. If r of t is differentiable and the norm of r of t, the magnitude, is constant for all t, then r of t dotted with r prime of t is going to give us 0. Now, why do we care? What does it mean when we dot and we get 0? Yeah, the vectors are perpendicular. So what this is really telling us is that r of t and r prime of t are orthogonal vectors for all t. Okay. Questions now? Jelly?
For number 6, is that f prime of t dotted with u or just multiplied?
Dotted. Yes. No, multiplied. I lied to you. Multiplied. Because this isn't a vector. So we can't dot them. Okay. Ready for some more examples? Great. Okay, example 4. The graphs of r1 of t and r2 of t intersect at the origin. Find the degree measure of the acute angle between the tangent lines to the graphs of R1 of t and R2 of t at the origin. R1 of t is the following. R2 of t is the following. Okay, so there's a lot going on. First thing we're told is that the graphs intersect at the origin. So eventually we're going to need to know what t is. So we got to figure that out. For the first graph, the point that's at the origin comes from t equals what value? 0. Inverse tangent of 0, 0, sine of 0, 0, and then 0 squared is obviously 0. Second graph, origin is at t equals what? 1. Okay. Next thing, we're finding the degree measure of the angle between the tangent lines. The direction of the tangent lines is the derivative. So we're going to have to find the derivative of both of these. Derivative of inverse tangent. It's 1 over something. Yep, 1 over 1 plus t squared. Derivative of sine is cosine, and then we have 2t. This next one we'll get 2t minus 1, comma 2, comma 1 over t. Next, we're going to plug in those t values. So here, plug in 0. We're going to get 1, 1, 0. Make sure for the second one you're plugging in 1 this time, not 0. You're going to get 1, 2, 1. So that'll be the direction or the slope of the tangent line. How do we find then the angle measure between those two? Yeah, do you guys remember the cosine of theta? In the numerator, you take the dot product. So in this case, 1 plus 2 plus 0. Denominator, this one's going to be the square root of 2. This one will be the square root of 6. So we get 3 over the square root of 12. So 3 over 2 root 3. So root 3 over 2. Theta then ends up being pi over 6, or 30 degrees. Okay. Are we ready to keep going? I know this is a lot, but if we get through more now, it means you have a shorter video tonight. So can we do one more example? Great. Thank you for having such a good attitude about it. Okay, last example, but this one's going to be a long one, just to tell you. We are going to calculate the derivative with respect to t of r1 of t dotted with r2 of t. We are also going to calculate the derivative of the cross product of those two. By differentiating the product directly and then again using formulas. In other words, those two formulas I put on the previous page. R1 of t is 2ti add 3t squared j add t to the third k. R2 of t is going to be t to the fourth k. We are going to start with the dot product. So differentiating the product directly, what I mean is find the dot product and then take the derivative. So if we do it directly first, we are dotting 2t, 3t squared, and t to the third with 0, 0, t to the fourth. Kind of nice, we get 0, 0, and then t to the seventh. So we get R1 of t dotted with R2 of t to be t to the seventh. And then you're going to take the derivative. And get 7t to the sixth. Okay, that's what I mean by directly. I'm also going to ask us to use a formula to do it. If we use a formula, we're going to take R1 and take the derivative and dot it with R2. We'll add that to R1 dotted with R2 prime. Okay. If we take the derivative, bless you, of R1, we get 2, 6t, 3t squared, dotted with R2, so 0, 0, t to the fourth. Then R1 stays. You're dotting it with the derivative of R2, so 0, 0, 4t cubed. So here we get 3t to the sixth. Here we get 4t to the sixth. So our answer then, which we already knew what we were going to get, is 7t to the sixth. Okay, I wanted to show you how to use both of these. I will not force you to use one over another. So if you don't ever want to use this formula and you always want to find the dot product and then take the derivative, that's fine. Sometimes the formula is faster. In this case, you can see it's not faster at all. So it just depends on the problem. I'm not going to force you to use them. I will ask you to know that formula, though. So on a test, I could use it on a true-false question, for example. Questions about dot product before we do the cross product? No? Okay, so let's do the cross product, and then we're done. Okay, if we do it directly, you're going to start by finding the cross product of R1 crossed with R2. Okay, so R1 is that 2t, 3t squared, t to the third, and we get 0, 0, t to the fourth. So in this case, we get 3t to the sixth minus 0. Oh, sorry. For the j's, we get 2t to the fifth, but with j, you have to flip the sign. With the k's, we get 0. So then you're going to take the derivative. As we already saw, you can just take the derivative of each component function individually. So we will get 18t to the 5th, negative 10t to the 4th, and 0. Okay, that's directly. For the formula, we will do r1 prime of t crossed with r2. Then we will have r1 of t crossed with r2 prime of t. So in this one, we're going to have to take 2 cross products. For this first one, if I take the derivative, I get 2, 6t, 3t squared, and 0, 0, t to the 4th. And then I get 2t, 3t squared, t to the 3rd, and 0, 0, 4t cubed. Okay, so ignoring the i's, we get 6t to the 5th minus 0. For the j's, we get 2t to the 4th, but remember you are flipping the sign, and then we get 0. Over here, we get 7t to the 5th. Nope, 12t to the 5th. And then 8t to the 4th, but flip the sign. And then 0. So finally, it gives us 18t to the 5th, negative 10t to the 4th, and 0. Okay, so this is the case cross product where I think most of the time it's easier just to find the cross product and then take the derivative, because you're only doing one cross product versus doing 2, but it's a way to check your answer, and it's another option if you think that that's easier. What's important to notice is that when you take a derivative of a cross product, you're going to get a vector, which makes sense. Cross product is a vector. When you take a derivative of a dot product, though, you're going to get a constant or an expression. How do we feel about the derivatives of vector-valued functions? Okay, is it bad, or is it just that we don't super well remember derivatives? Because you guys are looking at me like you're a little overwhelmed, but I have a feeling it's because